Hello. So I'm making this video to derive the expression for centripetal force in a simpler way. So when I was in 11th and when I came across this concept of centripetal force, I was very confused because what it basically says is if a particle is moving in a uniform circular motion, then it is subjected to a constant force which is directed towards the center and it is given by F is equal to mv square mv square by r, sorry. So what was very counterintuitive was that the speed of the particle is not changing at all, and there is no specific thing in the center that is attracting it. I mean, when the particle is moving in the center, sorry, moving in the uniform circular motion, it is not moving towards the center or away from the center. So one might think if there is certain force towards a certain point, then eventually that object should move towards that point. But in centripetal force, the object actually never, in case of uniform circular motion, the particle never actually ends up travels towards the center. So that was quite counterintuitive. So there's an example. So if you are riding a bicycle and you take a turn like this, then apparently you are constantly subjected to a force that is directed like this towards the center. Although there is nothing in the center that is actually that will actually attract you there, and you never actually go towards the center either. You just make a circle around it. So why would we say that the force is towards the center? The motion is not towards the center at any given instant of time. Motion is always tangential to it, tangential to the curve you are following, and then you never actually go to the center. Then why the force is towards the center? So and the proof given in 11th standard textbook is very lengthy and it uses a lot of vectors and everything. So that's why I wanted to make this video. So let's go into it. So we have taken a particle here. Good. Sorry. Yeah. So we have taken a particle here that is initially at this point, and then it travels a finite distance of angular displacement theta. So initially its direction of motion is along this arrow. This direction we are calling I cap. Now you will again say ki there is a lot of mathematics involved in this. You are introducing vectors. Actually, stay with me. It is not that hard. So okay. So for simplicity, we are calling this direction I cap direction. Then after some finite time, it travels some finite angle theta and ends up here. Now again, its direction of its velocity is somewhere here. So you see, its direction was initially here and it has changed. So there must be something that changed its direction. That's what actually we call the centripetal force. So now actually, if we try to decompose this vector in its components, then its component parallel to I cap, which is drawn by this arrow here. Since this angle is theta, this also becomes theta. So that is v cos theta. So initial magnitude and direction, initial velocity vector is vi is equal to v I cap. Then after the finite displacement theta, it becomes vf is equal to v cos theta I cap and v sin theta j cap, which I haven't constructed, but it's not really necessary to construct it here. So anyways, so v cos theta minus, sorry, plus v sin theta j cap. That's its final velocity. Now, what is the definition of acceleration? Acceleration is nothing but change in velocity per unit time. So this a is equal to v final minus v initial upon t. Actually, this should be delta t, so time interval. And as we know, if it is following some uniform circular motion, then this theta that it traveled, it would be omega times delta t. Sorry, let me fix it. Actually, we can call this delta omega as well. So delta omega is equal to omega delta t. So we can replace this delta t with delta omega, delta theta by omega. Then we can write this expression. A is equal to V cos theta I cap plus V sin theta j cap minus V I cap. And uh, now what we do is where the interesting part comes. So our statement was, whenever a particle is performing a uniform circular motion, at every instant it is subjected to a force directed towards the center, and which has a magnitude mv square by r. So what we mean by that is, not over a particular finite interval, but at every small instant it has this magnitude of force acting on it. So we are actually going to take the limit of this acceleration value as our theta or delta theta tends to 0, and then we can actually see at particular instant what its acceleration is and where the acceleration is directed towards. So let's see. So now, if we isolate the I cap and j cap, then we will get A is equal to cos this V cos theta and V cos theta I cap and minus Vi. So that becomes cos theta minus 1 I cap. Then this V omega I have taken common. Where does this omega come from? This omega comes from here. So delta t is we have written delta t is equal to delta theta upon omega. So delta theta upon omega, this omega comes up here. So it's V omega into bracket cos theta minus 1 I cap plus sin theta j cap. This was our acceleration. Now we take in the limit of theta tends to 0. Now it's the interesting part. So again, I have used the formula here. That simple formula is V is equal to omega R. So that V omega can be written as V is equal V square omega square R. Okay. Then as theta tends to 0, this expression actually converts into a derivative. So we have acceleration A is equal to omega square R into d of cos theta minus 1 upon d theta I cap plus d sin theta upon d theta j cap, and theta value tends to 0. So now you can apply either L'Hopital's rule or just by your usual derivation you do. We know that cos theta minus c, cos theta as theta tends to 0, cos theta tends to 1, cos theta minus 1 tends to 0, and d theta obviously it's in the limit theta tends to 0. So this is 0 upon 0 format. Similarly, sin theta tends to 0 as theta tends to 0, so this is also 0 upon 0 format. So we can use L'Hopital's rule, or you can just use your usual trigonometric limits to evaluate that this limit or this differentiation tends to 0. Similarly, this tends to 1. So what we are left is with A is equal to omega square r, and again using that formula V is equal to omega r, we can say that acceleration is V square by r. And by the way, V square by r in what direction? Since this component vanishes and we are left with this component, because this tends to 1, we are left with j. So I should yeah, I have written j here. So your acceleration is actually V square by r j cap. It is not I cap. It is not some random direction. It is specifically j cap. And what was j cap? J cap was the direction. Initially, I have taken this as I cap. So j cap has to be direction perpendicular to it. So this direction is actually j cap direction. So it turns out that although the particle is not really moving towards the center, its velocity is perpendicular. Its velocity is perpendicular to the line joining the point itself and the center, and it never actually reaches the center whatsoever. Still, its change in velocity is always directed towards the center. That's the beauty of this. So finally, we get the expression A is equal to omega square r or V square by r j cap. That's why when a particle is performing uniform circular motion, its force is given by F bar is equal to m a bar is equal to m v square by r n cap. Now here I am replacing j cap with n cap just to generalize, and n cap always n cap is the vector joining the point or the mass, let's say mass and center. And one more thing I would like to emphasize here is that in this derivation, as we take the limit theta tends to 0, it is not really only confined to uniform circular motion, because when theta tends to 0, your constant angular velocity omega is actually the instantaneous angular velocity. So it could be any path like this. It could be, wait, yeah. So if your particle is having some random trajectory like this, and at this point it is traveling in this direction, and it has angular velocity omega with respect to some center. If we calculate the trajectory, and you will know the center, radius of curvature, etc., etc. Then even this is not a uniform circular motion. If it has omega angular velocity with respect to this center, then you can say that this particle experiences this force towards this center, which has magnitude mv square by r. So, oh, sorry. So this result is generalized because we took the limit theta tends to 0. Okay, thank you.